In this video, we're discussing triple integrals, and we'll finally do a mass example. This time the example will be in cylindrical coordinates, and then we'll discuss writing triple integrals in spherical coordinates, which are appropriate when we're integrating over a region that has symmetry about a point rather than a line. So here is our mass example. It says, suppose the density of a solid suppose the density of a solid bounded by z equals x squared plus y squared and z equals 8 minus x squared minus y squared is proportional to the squared distance from the z-axis. Find the mass of the solid by setting up and evaluating an integral in cylindrical coordinates. And of course, because they say cylindrical coordinates, we know we're setting up a triple integral. Now, the first thing we need to do is realize that we are finding mass. So that's the first thing that stands out to me, is it asks me to find the mass of the solid. So I'm going to write down my general formula for mass. If density is mass per unit volume, if I take my density as a function of x, y, and z, and I multiply it by a volume piece, that mass per unit volume times volume will give me a tiny mass, mass of one little tiny cube. And then we're going to add those up and take the limit as the number of subdivisions in the x, y, and z directions all go to infinity. And that'll give us the exact mass of the solid. So we're setting up a triple integral over Q of this density function. Now, they did not give us the density function exactly. We have to derive the density function from the problem statement. We just have to remember a couple of little facts about proportionality. So this says, suppose the density of the solid bounded by these surfaces is proportional to the squared distance from the z-axis. So they're telling us the density, that's our row of x, y, z, is proportional to the squared distance from the z-axis. Okay, now this is a little bit contrived, because that tells me that on the z-axis, there is no distance from the z-axis, so it has zero density on the z-axis, so it really doesn't make any sense. But this is enough information for us to write down this density function. We're told, that the density is proportional to a distance from the z-axis, and we can find that, a squared distance from the z-axis. So let's just talk about what the square distance from the z-axis would be for a general point x, y, and z. So if I'm over here at the location x, y, z in three-dimensional space, the distance from the z-axis it's the shortest distance from this point to the z-axis. Now, it's really hard to tell where that XYZ is located. Maybe it's right here. Maybe it's above a point Y, or above a point XY, XY0 in the XY plane. And then we go up Z units to get to that point. Okay. Okay, so we're right here. This is where we're orienting ourselves in space. We're at this location, and we want the shortest distance to the z-axis from this point. Now, the shortest distance from the z-axis to this point, or they say the squared distance to the z-axis. There are lots of distances to the z-axis. I could take the distance from here to the origin, or from here to a point above or on the positive z-axis, or from here to a point on the negative z-axis, which would be down here. All of those would be options for distances between this point and the z-axis. So you have to remember, when you're in Calculus 3, if somebody asks you for a distance from a point to another line, or a point to a curve, or a point to a surface, what they're usually asking for, or they're almost always asking for, is the shortest distance between the point where you are and that line or surface that they're discussing, the line or surface that they're mentioning, talking about. So the shortest distance between this point and the z-axis, it would have been better if I had done a better job with my picture. The shortest distance is this distance from here to here. It's going to be a horizontal distance, and it's going to go straight from the z-axis to this point. So it's going to go straight from this location, which is at x equals 0, y equals 0, z equals z, to that point. I hope you guys see that the distance from here to here is r. And you're like, what? It's r? Let's think about it. What's the distance between this point and this point? Well, remember how we find distance between 2 points, or alternatively, you could create a vector from here to here and find its length. Same thing. We're going to subtract the coordinates. We'll have x minus 0. Oops, I'm writing z. X minus 0 squared plus y minus 0 squared, and then z minus z squared. Z minus z squared is 0, of course, so we end up with the square root of x squared plus y squared, and the square root of x squared plus y squared is r squared. So the distance from this point, or the shortest distance between this point and the z-axis, is just r. Now go back to the problem statement. It says, suppose the density of this solid is proportional to the squared distance, the shortest squared distance from that point to the z-axis. So we don't actually, the density is not actually proportional to the distance. The density is proportional to the squared distance. Now remember what proportional means. This is just a quick review. We said that y is proportional to x many years ago when you learned about variation. We said that that meant that y was a constant times x, where k is some constant of proportionality to be determined by us. If we had an xy pair, we could find k. So when they tell us that the density is proportional to the squared distance between that point and the z-axis, what they're saying is that this density is equal to a constant times the squared distance, that distance to the z-axis. And the distance to the z-axis is r, what we know as r in cylindrical coordinates or in polar coordinates. This is k times r squared in terms of r and theta. Or in terms of x and y, well, I would just take this version and I would square it. So we have that. So either this one or this one would be fine. This is our density in rectangular coordinates. And then this one is our density in polar coordinates or cylindrical coordinates. Okay, so now we've got a function to integrate. That's our integrand. So our mass is the triple integral over Q of the density, which we just found. We're going to go to cylindrical coordinates. I know that, so I'll call that kr squared. Density times dV. Now, in order to evaluate this integral for mass, we just need to find a way to describe the solid region Q. And we need limits of integration, and then we'll just integrate from here. Okay, so let's see. How did we set up this problem? The first thing we did was we wrote down our mass integral. So we state the formula for mass, because that's what we're asked for. And then we had to translate this English sentence, this green highlighted sentence, into a density function. So we use the given information to find the density function. And that required remembering the distance between 2 points, that required some idea of what is meant by a distance between a point and a curve in three-dimensional space, and what that means is the shortest distance generally. And then we get that density in terms of x and y or r as appropriate, using this idea of proportionality. We say that y is proportional to x if y is a constant times x. So we put all of those together and we get our density function. And now we're here. So we substituted our density function into the integrand. And now we want to come up with appropriate bounds for our solid. Excuse me. Okay, so our solid, they told us at the very beginning, was bounded by z equals x squared plus y squared and z equals 8 minus x squared minus y squared. So we need to sketch those surfaces. It's always a good place to start. And then we use our sketch to come up with the appropriate bounds for Q, the solid region. I notice right away that z is raised to the first in both cases. X and y are both squared. Both of these are positive, and both of these are negative. Since they're both squared and they have the same sign, these are elliptic paraboloids. This is just my standard elliptic paraboloid facing up. It's going to look like this. And this is an elliptic paraboloid facing down because I took this equation and I multiplied it by -1, that flipped it upside down, and then I added 8 to it, which shifted the whole graph up 8 units. So I've got one elliptic paraboloid facing up, another one facing down, and they're going to come together to look something like this. This is, of course, not to scale. And it should join a little differently. Shouldn't have those weird sharp corners on it. But that's the idea. So how are we describing Q with the appropriate bounds? The first thing we do is we sketch Q. So this is Q. I notice that my bottom function for z is x squared plus y squared, and my top function for z is 8 minus x squared minus y squared. So right away, I see my bounds for z are from this function to this function, from the bottom function to the top function. And then I have to think about, okay, once I've sketched Q, I need to think about the projection of Q onto the XY plane. Well, I can see the projection is going to be defined by that circle where they meet. Looks like a circle, doesn't it? Maybe it's an ellipse. I think it's probably a circle. If I took the sun, and if the sun is right here, that sun is going to cast a shadow on the XY plane. That shadow is the projection of that surface onto the XY plane. We call that the region R. So we need to find the boundary of R in order to sketch R. And the boundary of R comes from setting the z value on this surface equal to the z value on this surface. That's going to be the equation of that curve. It's going to be that curve lifted up so many units. But then when I take the projection down, that curve is going to become that curve when I take the projection onto the XY plane. So we've got bounds for z, and I guess I should say this is from the bottom function to the top function. And now we need to describe the region R. So we sketch Q, sketch the projection R onto the XY plane. And then to find the boundary of R, we set this z value equal to z value and solve. Actually, I think I'll have enough space here to do that here. So I'm setting the top function equal to the bottom function. So that's x squared plus y squared is equal to 8 minus x squared minus y squared. I guess I set the bottom function equal to the top, same thing though. Add the x squared plus y squared to both sides. So you end up with this over here. So I end up with 2 times the quantity x squared plus y squared equals 8. Let's divide both sides by 2. And we get x squared plus y squared equals 4. That's nice and easy. The boundary is a circle of radius 2, centered at the origin. So that is our region R. Okay, so I've got bounds for Z, and I look at my region R clearly. It's easiest to describe in polar coordinates. It's a part of a circle. It's actually an entire circle. And also, if we look at this solid Q, we can see that we have symmetry about the z-axis. Since there's symmetry about the axis and axis, cylindrical coordinates are probably appropriate. So let's find the appropriate bounds. So we said already that z goes from this bottom function to this top function. And I factored out that -1, so I see that x squared plus y squared. Now remember, if we go to cylindrical coordinates, x squared plus y squared is equal to r squared. Okay, so those are my bounds for z. So this is, again, going from the bottom function to the top function. And then I look at my circle, centered at the origin with a radius of 2. And remember how this works in polar coordinates. R equals 0 is right here. R equals some number is right there. R equals some number is right here. And as R increases from 0 out to 2, we're going to get all of that. We're going to get that solid disk from 0 to 2. Now, you would not necessarily have to get the entire disk. We only get the entire disk if theta goes from 0 to 2 pi. If theta went from 0 to pi over 2, we'd get that quarter of a disk. Or if theta went from 0 to pi, we'd get the top half. Or pi over 2 to 3 pi over 2. And there are lots of different possibilities here. But I want to think of R as, or values for R like this, as concentric circles radiating out from the origin. So R equals 0 is here, and then R equals 2 is here. So it's going from 0 out to 1, then to 2, okay? And so we get this. So R goes from 0 out to 2. And then meanwhile, at the same time, theta is an angle that sweeps around the xy plane. So theta starts here and ends here. On the x-axis, theta is 0. Then we go all the way around 360 degrees or 2 pi radians, and we end up over there. So these are our bounds for r and theta. They're constants. So now we've got our bounds for our triple integral. Z goes from a function of r to a function of r. So we have to integrate with respect to z before we integrate with respect to r. And r goes from a constant to a constant, and theta goes from a constant to a constant. So it doesn't really matter what order we do those, because they don't depend on each other. Neither the bounds for r or the bounds for theta depend on the other one, depend on the other variable. So let's go back to our mass integral. Our mass integral is the triple integral, excuse me, of the density function, which we found earlier to be kr squared. in cylindrical coordinates. And now we've got bounds for r and bounds for z, r and theta. So we can set up this integral. Z goes from r squared to 8 minus r squared. So we integrate with respect to z first. And then r goes from 0 to 2 pi, or 0 to 2, and theta goes from 0 to 2 pi. So we'll integrate with respect to r next and theta next. Now don't make the mistake that it looks like I almost just made, okay? You need bounds. In cylindrical coordinates. You need the integrand, which happened to be the density in this mass example. In cylindrical coordinates. And then you need dv. But remember that dv is not this. dv is dz, so we had a tiny change in z, times dA, where that dA was the dA in polar coordinates. So we have dz times r dr d theta. That r is a part of our dv, because dv is, that's our third dimension dz, and the dA, that area that little area piece that we're seeing in the xy plane, is given by r dr d theta. Okay, so we've got a new dv, we've got an integrand in cylindrical coordinates, and we've got bounds in cylindrical coordinates. I lost an s for some reason. Okay, so that is our triple integral. Now let's evaluate it. So I'm ignoring these integrals on the outside at first. And I'll simplify that integrand. That's k times r cubed. And initially, we're just focused on the inside, innermost integral first, and then we work our way out. Okay. So this stuff on the outside, I'm bringing it along. I'm not doing much with it, though. I just leave it alone. The antiderivative of k times r cubed with respect to z, that's all constant with respect to z. So we get that constant times z, and we evaluate from z equals r squared to z equals 8 minus r squared. So that's our first step. What did we do? We were anti-differentiating with respect to z. And then we use the fundamental theorem. Evaluate at the upper limit and evaluate at the lower limit and subtract. So z is being replaced by 8 minus r squared. And then we subtract and we replace z with r squared the second time. R cubed times r squared is going to give us an r to the fifth because we add those exponents together. So we're here now. And we should simplify this. So I've got 8 times k r cubed minus, I distribute, k r to the fifth minus another k r to the fifth. So I guess I've got 2 of those. Still simplifying. Okay. And now we anti-differentiate with respect to r. So we do the next integral. K is just some constant of proportionality. I don't know what it is. So we just treat it like a constant. the antiderivative of a constant times r cubed with respect to r comes from bringing the constant down. Then you add 1 to the exponent and divide by the new exponent. Then over here, we bring the constant down, add 1 to the exponent, and divide by the new exponent. Substitute in 0 for r and 2 for r, and subtract. That's from the fundamental theorem. And of course, we could simplify this. 4 goes into 8 twice, 2 goes into 6 3 times. So I've got 2k times 2 to the 4th. 2 to the 4th is 2 times 2 times 2 times 2. Did I say it 4 times? I hope I did. 16. 16 times 2 is 32. And then over here, I've got 1/3 of k and 2 to the 6th, that's 64. And then we evaluate all of this at r equals 0, but that's just 0 minus 0, which is of course 0. So now I've got this, which is all constant with respect to theta. So we're just going to get this times theta and evaluate from 0 to 2 pi. Just do a little bit of arithmetic. Let's factor out the k. This is 32 over 1. This is 64 over 3. And I'll multiply by 3 over 3 here. That's actually 32 times 2. So we're going to get, oops. And the antiderivative of that with respect to theta is theta. Still doing my arithmetic. I end up with 32 over 3 times k. And then we multiply by theta, where theta is evaluated from 0 to 2 pi. So we get 2 pi minus 0, or 64 pi times k over 2. That's going to be the mass. I don't know what that constant of proportionality is, but that represents the mass of our solid that lies between those two surfaces. Let's go back to this picture. It's the mass of this solid that lies between these two surfaces, provided that the density is proportional to the squared distance between any point within this solid and the z-axis. Okay, and what did we do at the end? We anti-differentiated with respect to r and used the fundamental theorem, and then here we anti-differentiate with respect to theta. And then we use the fundamental theorem and simplify to evaluate it. Okay. So that's mass. I think I am going to save triple integrals in spherical coordinates for another video. So we'll do that next time.